Hello everyone, welcome to our privacy and security midterm representation. Today we'll be talking about deep learning and with differential privacy. My name is Yuchen Lin and I will be your presenter today. And our team name is www. Here is our outline. First of all, let's talk about what differential privacy is. Differential privacy is a mathematical rigorous framework that allows us to release statistical information about data while protecting the privacy of individuals. Traditionally, differential privacy has been applied to complex models. However, the methods introduced in these papers can handle non-convex models. Deep architectures and even models with tens of thousands to millions of parameters. The CIFAR-10 data contains 60,000 color image size, 32 multiplied 32 pixels, divided into 10 classes with 6,000 images per class. Of these, 50,000 images are used for training and 10,000 for testing. The MNIST data is a well-known collection of handwritten digits, often used to train image processing models. It has 60,000 training images and 10,000 testing images. All images are black and white and have been normalized to 28 multiplied 28 pixels. For any two adjacent inputs D and D prime in D, and for any possible subsets of the outputs S is in R, the probability that N of D produce an output in S is nearly the same as the probability that N of D prime does. The condition is formalized by following inequality. The core idea of these paper methods is training a model by minimizing the empirical loss function L's of zetas, where zeta represents the model parameters. During each step of the stochastic gradient descent, first steps, random subsets of data is selected, and second, for each example, the gradients of the loss function with respect to zeta for input x is computed. Then we clip the L2 norms of each gradient to limit sensitive, and the average gradient is calculated. Noise is added to the average to ensure differential privacy. Finally, the model is updated by moving in the opposite directions of the noise gradient. At the end of training, the methods not only output the final models, but also calculate the total privacy loss using a privacy accountant. The first method we use is a fully connected neural network applied to the MNIST data. In the models, each image is first flattened from a 28 multiplied 28 matrix into a 784 dimensional vectors. The output is then passed through one or more fully connected hidden layers with ReLU activation, expanding from 784 to 1000 dimensions. Finally, the output layer reduces the features to 10 dimensions, corresponding to the 10-digit classes in MNIST. To ensure differential privacy, we apply gradient clipping aids Gaussian noise and also incorporated principal component analysis as a processing step. This method was implemented and evaluated on MNIST data. And the next slide will present the specific parameters we used. We also use resonate models, which is a convolution neural network architecture that incorporates residual connection to enable deeper and more stable training. Each residual block consists of two convolutional layers, both using 3x3 kernels, followed by group normalization and ReLU activation functions. These models was applied to the CIFAR10 dataset, which include color image classified into 10 categories. Training setting include batch size 100 APAS. Epsilon is 8.0 and delta to 1 times 10 to the powers of -5. We apply gradient clippings with a L2 norms threshold of 5. The learning process used a learning rate of 0.1, momentants of 0.19. Now let's talk about the results of applying a neural network to the MNIST data. In your graph, the y-axis represents training accuracy, and the x-axis shows the numbers of APAs. The blue line represents the model's trends without differential privacy and without PCA, while the green lines show the model without DP but with PCA. From these two lines, we can see that PCA doesn't improve training accuracy when DP isn't applied. The yellow and red line represent models trained with differential privacy. The red line includes PCA, while the yellow one doesn't. Also, applying PCA may slightly reduce the accuracy during training. We observed that training with both DP and PCA coverage faster than DP alone without PCA. Now let's move on to CIFAR10 result using Resonate 20. In these charts, the y-axis represents accuracy and x-axis show for evaluation setting, training with differential privacy, testing with differential privacy, training without differential privacy, and testing without differential privacy. When we apply differential privacy during training, the model achieves 64.01% accuracy on the training set and 62.23% on the testing set. In contrast, when training without differential privacy, the model reached 96.01% accuracy on training sets and 79.01% on testing sets. This shows that applying differential privacy significantly reduced model accuracy, especially for more complex data like CIFAR10. And this is our reference to this, and thank you for listening.